Welcome to ITS 2010. We're commencing Module 5. This is the concluding module of the book. Your reward for this is that we only have 3 units. Kind of sort of following the book, we are aligned, at least emotionally, with Chapter 6, entitled The Data Link Layer and Local Area Networks. We're going to approach it a little bit differently, so I can cover kind of what you need to know. I can motivate you for what you need to know by looking at Layer 2 as a series of problems that we need to solve based on the concepts that we've learned to date. Then going on to the modern technology family that's used to implement Layer 2. And then we can, through the eyes of Professor Bonaventure and your instructor, and not Kevin Kelly so much, look at the kind of the technologist's view of the future for the internet. Realizing that we had a choice, I had a choice anyway, to organize the class as layers progressing 1, 2, 3, 4, 5, or 5, 4, 3, 2, 1. Honestly, either one would have worked. The fundamental idea, though, is that it is the study of software. Year over year, thank you Moore's Law, year over year, the hardware is less relevant. The network routing and switching hardware all uses the same chipsets as do the laptops and servers and desktops everywhere. There's precious little that doesn't run on the Intel processor these days. So other than like the specific Nobel Prize worthy physics that gives us increasing data rates year over year, and those fiber optics and wireless, for the most part, it's just a computer, and the things that we talked about in layers 3 and 4 are just program features. Now, there are so many program features in the internet that we cannot just indiscriminately study them all as one great big body of software. We divided them into parts, and the parts implemented this notion of the service model, or the layered service model of protocols, such that, just the way we have chosen to draw this, the lower layer subordinate serves the upper layer superior. It's a hierarchical approach. It's arbitrary, but it's what we did. We started with 2 layers, then we took, the infrastructure substrate and cut it up into a bunch of different layers. And we didn't need networking in order to take on a layered approach. But having already understood that operating systems provide the services to applications, that at various levels of abstraction, we can perceive that applications talk to applications. Which is layer 5, we can perceive that the transport layer, TCP, operates end-to-end across an opaque, mysterious, ever-changing cloud. We can, which is layer 4, we can look at layer 3 and understand that this system of global addresses, which is completely consistent with host names and IP addresses, is completely and totally necessary. Oh, and by the way, at some point we have to figure out how to connect 2 devices directly together over a network. So that's kind of where we are today. It's what I call on slide number 2, it's our destination. We've mastered some really complex, complicated ideas, and the last piece of our puzzle is what exactly is used to connect 2 things together. There had at one point been kind of an 80-20 rule, 80-20 also known as Pareto's law. There's a Pareto distribution. In the old days, 80% of the traffic started on your network and ended on your network. At some point, the Pareto relationship flipped, and that, essentially most of the traffic in some organizations exits the premises, exits the company, and goes someplace else. Definitely true for OU, because Blackboard happens to be operating at blackboard.com in Northern Virginia. And so our Office 365 Exchange cat mail runs in the Microsoft cloud. I have no idea where. Nobody knows. Somebody knows. I don't know. So our 80-20 rule is that, we We sometimes save our files locally on a common file server that's on our own campus, although we really don't anymore. We kind of sort of print to a printer that's down the hall from us. I think that's still true. And we all connect wired or wirelessly through something in our own building in order to reach the next node and touch the gateway that connects us to the internet. These aren't happy people, and education is a challenge, and it's never good in your organization where you're discussing Russian novels and discussing Russian politics. But I couldn't help but look at I believe they're called Perestroika dolls, or Russian nesting dolls. That's Lenin, Brezhnev, Yeltsin, Gorbachev, and Putin, the little guy. And the political interpretation is you open one up and you simply find the next one, and they're all basically the same character. I can't comment on that, but we use this notion physically of encapsulation to show how layer 2 frame data, with some addressing, and for the first time something I'm going to call a footer or trailer, encompasses the entirety of the layer 3 packet, which includes an IP header where the addresses live, and some IP packet datagram data. And we can similarly have UDP and TCP header and data and a little bit of data. If you would look at this drawing on slide 2 and take it literally, you would say, well, the data is like the size of one square, and by the time we get into layer 2, it's like 4 out of the 5 squares are like headers and footer. It's not exactly true. It still comes down to the fact that the frame can hold about 1,500 characters. And of the 1,500 characters, typically, like 40 to 60 of those characters are header, and the rest of it is frame data. So we really do have a great big envelope to hold a lot of stuff. 1,500 characters is like half of a page of typed text, to put it in perspective. So we're going to approach layer 2 as the solution to problems that, first I'll kind of warn you that we have the problem, then we'll go ahead and kind of fix it. That, if I, again, look at the principles of our layered service model protocol, TCP, that the end-to-end reliability is needed because the expectation is that every character of every sentence of every paragraph sent will be received regardless of what kind of device it is, regardless of where it is. So we will leave behind no letter, word, sentence, paragraph, page, no pixel, no decimal point, no character, no number. That's layer 4. Layer 3, the global internet, requires datagrams, messaging, and routing. It requires that the addresses be globally recognized, globally unique, at least in terms of the addresses that are shared across the global internet. We simultaneously support the use of domain names and host names within that structure. We're good with that. That's it kind of is the essence of our duality, that it looks like it works one way, but it's really something else. The internet, however, as we get to layer 2, requires access. It should require access from our home or our desk to our enterprise network. It intrinsically is based on how to connect two nodes. Node can be a terminal node, which encompasses printers, computers, laptops, handhelds, etc. It is the foundation for connecting, meaning interconnecting, and interoperating, meaning sharing data. That I can hand an envelope from one device to the next, and it will be properly processed and respected. And so, obviously, moving on to slides 3, 4, and 6. Actually, I need to take these in the order that I've displayed them, presented them. It happens that this notion PBL, I think that'd be a nice Section A kind of definitional sort of thing. It's true, not only do we learn through stories, but we also learn through case studies and problem solving. It happens that problem-based learning has been demonstrated to be very effective. It's not a technique that I've used in this class. It is kind of subtle. I have taken a couple classes with, in one case, with pretty good success, teaching every concept as the solution to a problem. Walk into class, here's our problem, let's solve it together in groups. I've also tried to teach in terms of cases. Our highly esteemed College of Business might only do a couple case studies per term, per semester in teams. For them, they had a great outcome. For me, the outcome perhaps wasn't so great. But the problem-based learning, I think, is really effective. If you can identify with a problem and you're reasonably creative, if you're willing to think inductively, to use everything you've used, it can be, in fact, a little bit of fun. So here's problem number one. And the inventors of the internet, just to be blunt, they did start and invented layer 1, then went 1, 2, 3, 4, 5, which is actually how they got their number. So we found that teaching-wise, we're saving you the problem, the pain of the problem solving. But the first thing they discovered when they went to send data, on real media, like coaxial cable, that there was a rate at which ones came out as zeros and zeros came out as ones. And that rate, it doesn't matter exactly what it was. Let's say it's 1 in 1,000. We got it up to like 1 in a million, and maybe we're up to 1 in a billion now, but it's a rate. The rate is never zero. It is what it is. And so we therefore always expect errors. We can never act surprised when errors occur. And so our design approach, our planning approach, needs to detect and mitigate these errors. Not a big surprise. The errors, not only are they real and concrete, if I am sending, let's say, a 6-slide PowerPoint and there's an error, the error actually occurs in specifically one line of one of the slides. So if there's an error, the error has position, it has place. Okay, so here's my ever-popular exercise, War and Peace. Back to the Russians, that we have, let's say it's 1,000 pages. If my error rate is 1 in a million, and the book is 1,000 pages, and each of the pages has 1,000 characters, let's do some really quick math. That if my object size is a million, and my error rate is 1 in a million, 1 over 1 million, and I multiply those two together, then the answer is 1, that I will describe as 100% or certainty. Do it again. I got 1 million characters in my book. That's true, I looked it up. And my error rate is 1 in a million, which is a fine copper-based local area network bit error rate. So 1 in a million times a million is 1, which means 100%, which means we are certain to encounter errors. Now, the thing that we can use to our advantage is that the error has a position. The error's on page 123. Okay? So in this particular case, if 1,000 pages, if 1,000 characters each, and the error is going to be on one of those pages, then that's the page I want to resend. The other 999 pages that are error-free, we detect that and we're happy. The page that has the error on it, we detect, we send it over again, and interestingly enough, when we send that page over again, its error rate is the same, 1 in a million. But this time, it's 1,000 characters divided a million, in which case the effective error exposure is less, because the object we're sending is a page, not a book. The actual likelihood of getting that in my little verbal story here, the likelihood that page goes through the first time with no errors is 99.9%. There's a 0.1% chance that that page will be flawed, in which case we just send it over again. And probably, what would that tell us? The first time error rate, um, well, the likelihood of a getting a pure send after one retry is 99.9%, which is like really great. Okay, so let's look at this again. Divide and conquer. The, the, the error rate is the same, whether it's large or small, but the exposure, which is the math product of the object size times the error rate in this case, means that the likelihood of sending something big and getting lucky with perfect transmission is not good. It's 100% likely to fail. If we give it one retry, it's 99.9% given that second try likely to pass. That's a beautiful thing. And that's because somebody observed that the error is on one page and not the others. And it's the only page that had to be resent. My doctoral dissertation, I don't know what it was, maybe it was 150 pages. In the year that I did it, I was asked to fax it. And so basically, if I put 100 pages into the thing and pressed the go button, and I would fax it to my advisor, who had since moved on to her new position as like dean at University of Colorado, it always failed. I was always trying to resend that thing. We didn't have the ability to do the email transfer. Okay, congratulations, you mastered how we harden ourselves against errors by inventing the frame. The frame is the notion of sending one page at a time. Slide number 4, error detection and correction. Well, in order for us to detect the page with the flaws on it and detect it and correct it through retransmission, we need a little bit of math magic, okay? And so the correction part of this is really straightforward. If you know page 123 is errored, has an error on it, is damaged, we ask for it to be resent. The detection part is actually quite interesting. That let's say somebody gives you a gift. Somebody gives you a gift, and you weren't expecting it. You don't know what it is, and when you open it up, you're not sure if it's exactly what was ordered or what was supposed to be sent. Perhaps we order through Amazon or whomever, and we have it delivered. So how do they know to put the right thing in? We actually don't. A recipient does not intrinsically know if they weren't expecting it, whether they got the right thing or not. We should pause and let you kind of restate that in English in words that work for you. But what we can do is we can treat the entire message as a number, and we can take that message, treat it as a great big long one-page number of ones and zeros, divided by a special number, and look at the remainder. I don't know. I mean, if we divide it by a number, then the remainder is smaller than that number. If we're going to divide by 10, then the answer is, a divisor and some remainder that could be from 0 to 9. What happens by doing that division nicely, there's somebody who got maybe not a Nobel Prize, but probably a dissertation or a thesis out of it. Somebody who determined what we needed to divide by in order to get a remainder that would tell us whether we were correct or not. And so the deal is, if you look at slide number 2, that frame footer contains the remainder of a certain special division, and the remainder is calculated by the sender, where life is good, put in the message, and transmitted. The receiver gets that same message, performs the same calculation, the same polynomial division, and gets a remainder. Well, it happens, this is a long story, I apologize. If the remainders are the same, there's no error. If the remainders are different, there is an error, and retransmission shall be summoned. It's called a longitudinal redundancy check, or a cyclic redundancy check, CRC or LRC. It's not like totally perfect, but it's amazingly accurate. And so there's magic in the number they divide by, and the receiver calculates it independently from the sender and compares the results. If the results are the same, it's no error. If the results are different, we'll use that scenario to declare an error. Oh, and you might say, well, what if the error actually occurred in the LRC, CRC, in the trailer itself? I refuse to answer that. That's an error that slips by. Okay. There are some codes in this that actually can say, well, that T on page 123 on line 6 needs to be a R, be an R. There are some codes that actually can correct errors. I'm not going to get into that, but the math exists. Slide number 5. I invented this in probably the first quarter that I taught. I said, I need a slide that kind of puts this all together. And let's look at just layer 2, which is devices that can see each other, that are like right next to each other. And how are we going to classify these things? Because classification, taxonomy, structure, I think is a really powerful way to organize our thinking. Psychologically, if we have a framework, such as like the layered protocol model, if we have a framework for organizing our thinking, then we have a place for each additional idea that we receive. So the framework part is really strong. It is, in fact, how we learn. Okay, so here's my framework. We've got topology, media, access method, and encoding. Every network that we talk about has got to check a box under topology, check a box under medium, check a box under access methods. And for layer 2, there's got to be an answer to how do you encode. So the basic topologies, which I believe I have shared previously, but those topologies also appear on slide number 6. You can feel free to look back and forth between 5 and 6. The bus, the ring, the star, which really is an asterisk, a mesh, the hierarchy, point to point, and of course in nature everything is like complicated, so there's hybrids that combine each of these sorts of things. There's a lot of stuff. The star is how we build our buildings. We typically have a closet, and from that closet there's a box, there's a switch or a hub, and it connects to a bunch of other devices, whether they're phones or wireless access points or computers or surveillance cameras or door strike relays or stuff like that. So the star really carries the weight, and we build stars of stars. Our campus is a star, where the hub is in like the main library up on President Street, Alden Library, and then it connects to a building, to every building, and so there's like 80 nodes on that star, and then every building has got one of these things on every floor of every building. So it's like Schoonover Center, where my office is, has 4 floors. So enter the building, and then you got 4 of those things, and then on each floor there's a branch to each of the jacks, in each of the offices. A star of stars of stars of stars. Then the medium, okay, plural media, classified as guided or unguided. Well, the unguided stuff is kind of like the intangible, which would be wireless, and there is a form of optical, which is just sending light through the atmosphere, which actually is done in some places. Okay, it has special powers, and it's not ever going to have interference issues like wireless radio does. The guided classifications are copper and fiber optics. The copper has 2 forms. The coaxial cable, coaxial means co-axis, same axis means got thing in the middle, insulator, woven or solid jacket or braided layer, and then the jacket around the coax. Coax like for cable TV. And the twisted pairs like for phone lines, a typical wired phone, if you could find one, takes like 2 wires. Typically the jacks will be set up for 4 wires. Typical household has 2 4-wire drops, and then there's lots of cable pairs, and so they would, in fact, when they're paired, they're color coded. The kind of modular jacks that are used in network apparatus, uh, whose terminations are called Cat5 or Cat6, that's kind of Unit 2 stuff, will have 6 of those 8 wires used for communications, and 2 of the 8 wires are used to deliver power, which is interesting. So we got coax and fiber optics. The fiber optics you will encounter by the color of their jacket, which would be orange, yellow, or kind of a baby blue. The it is completely reasonable to have fiber optics run, especially to a new building or a multi-tenant building, whether it's apartments or retail space, to 2 strands of glass, one to send on, one to receive on, and they are modulated by turning the signal on and off, kind of like Morse code. And so it happens that the glass, much like the human hair in diameter and physical attributes, can be bent. The issue is not that the glass breaks if you bend it. The actual issue with fiber optic media is that it uses a physical process called refraction. Light is kind of a particle and kind of energy, and so the energy can escape this thing that is the diameter of the human hair if the radius is too small, too tight. Okay, and so it's like if we just kind of loop our fibers, like at the diameter of, I don't know, a basketball, we will never have any problems with them. But actually, if you make the turn on fiber optics too sharp, the photons will escape. Now, don't ask me where they go, because I don't know where they go. They certainly escape. And where do they go when they escape? They go to Florida. I don't know where they go. Okay. So in any case, we have the fiber optics, and it's important. It's $50,000 a mile to run fiber optic networks, even when they're on poles, and it goes up from there if we're like trying to do it in high terrain or someplace complicated, and we cannot put power on fiber. Access methods, again, I have 3 flavors of this. This is important stuff. This is like really easy testable stuff. Okay, just kind of organize it with there. The access method, if I create a channel, whether it's an airwave or a piece of wire, I can either put some device in charge of telling other devices when they can speak, or we can let them kind of work it out on their own. Well, this method called polling puts a device in charge, and it tells it they can each send and receive at the same time, in fact. And in a hierarchical topology, the central device can be empowered to call on stations when they shall have permission to send. That's called polling, and there's something centrally in control. In the methods called contention and sharing, well, there is going to be a device centrally. So physically you can't tell by looking at it, but basically contention means fighting for access, and then there's a contention method which allows devices to shout until one gets its turn, and then there's another method that simply is taking turns. That you, if you can visualize kind of a logical topology that's a circle in the round, and people take turns going clockwise, taking turns to go send. It's interesting that the taking turns approach mathematically is somewhat superior. Plus, you can have like a great big circle and have lots of devices on it. It's fair because every device gets a turn, and if they have nothing to say, their turn is like really short. I'll pause there. So this token passing approach is fair. It kind of mentally aligns with the circle or ring topology, and it is fair, and on average it's somewhat efficient because you know when it's going to be your turn. Now the really advanced version of this allows several devices to be transmitting at once. So maybe chairs 4, 8, 12, and 16, contain permission to send at once, and they merely relay their message to the next device to them on the ring. It happens that is incredibly high performance. So we often call these sharing, not just taking turns, but token passing in the possession of the talking stick. The possession of this permission message means that a station can send. They only send clockwise to the next station, and it's amenable to an approach where multiple of these things can be going on at once. Very thoughtful, very effective. Kind of the people who did it got a little too greedy, and so their approach did not become the standard. The one that did become the standard is contention, which was within the network device. Basically, an algorithm that said, listen first, and if there's nobody else talking, go ahead and talk. And it works okay until it doesn't work. It works okay until you have too many stations on board, in which case you never really get a turn to talk. And that it happens that at a kind of a sub-microscopic basis, the time it takes for one station to send and the farther away ones to hear it becomes very problematic. And so we didn't, we did that for a while, and then mathematically it's a train wreck. Mathematically it's horrible. So I'll let you in on a secret. In unit number 2, we solved that problem separately. Okay, so contention sharing polling, guided, unguided media, bus ring star, etc. The encoding part I really don't want to get into. That's the layer 1. In layer 1 is not on our test. Layer 1 is the world that is unframed. It is messages that are just raw bits. And what I will mention is that information, which is the ASCII chart, from going from ASCII to binary to ones and zeros, well, whether those ones and zeros are like high voltage, low voltage, or laser on, laser off, or some phase shifting sort of thing, we are takers, not makers of that technology. So don't worry about it. Whether it's signal on or signal off or something more complicated, that's in the parts that we buy. It's not a decision on our part. All the devices use the same method, the same voltage, the same timing, all that stuff. Do I think it's interesting? Very much so. Is it worth taking up more than a minute in this class? Negative. Slide 6. And wrapping up. So we take these layer 2 concepts of error detection and error correction, of frames, of taking, experimenting with different topologies and access methods. Working with coaxial cable was horrible because if you disconnected one place, you took out everybody else downstream. Rings, were kind of built on coax. They didn't really particularly go well either. So, there's a lot of learning that took place when people started connecting 2 devices together. They had a lot of options. How can we array them to get better performance? How can we organize permissions so we can utilize it a lot, but not utilize it so much that messages are colliding with each other? So it happened that these folks started the path toward connecting 2 devices together in a concept called local area networks, like a decade before the internet stuff, but a decade before the internet people got together. You probably can't imagine this, but a laser printer that cost $10,000 in 1983 dollars, a file server for file sharing and centralized backups might have cost $50,000 in 1983 dollars, and they were deemed to be a tremendous value. Okay, and so what if we couldn't trade messages with people, with our friends, in our supply chain, with the other departments in our company? We didn't need any of that stuff. So the working LAN stuff it preceded the internet by a decade. It was deemed successful on its own merits, beforehand. We had the ability not only to share files, but to share applications. One of the first applications out of the chute was email within a company. back to the 80-20 rule where 80% of the traffic stayed inside the business, it was very successful. There are organizations that are in, several cities, several states, several countries, several continents, and just being able to message people within your own organization, again, great value proposition. Printer sharing backups, um, bullet number 3, surplus cable TV cable, surplus like radio coaxial cable was the basis of networking, and or the guy who really led this field, Mr. Metcalfe's law came up before, took the onerous, difficult problem of connectivity between the Hawaiian Islands, which is where he discovered actually one of the principles that we'll cover in the next unit. So the wireless connection between islands did kind of fit the model of the local area network. It had all the same problems that locality had. It was a closed system. So here's kind of a riddle. When we first started building these things, what constrained the size? What really stopped us from building one local area network that connected all 80 buildings on campus? What was it? Was it the signal strength, or was it something else? Well, the kind of reflex thought is it was the signal strength, that for some reason the signal level would diminish, would attenuate, would be noisy, get interference, and that we couldn't send a signal that far. Well, you know what? We can put an amplifier on a signal and broadcast to Mars. So it really wasn't the signal thing so much. It was the upper limit on the time it would take to go from one extent of the network to the other extent of the network. And that, when we adopted contention, which is basically no station in charge, no hierarchic, no turn taking, stations that would listen first, then send. Well, you know what? The time it took to get from the signal, even at the speed of light, to get from the other end of the network from that end of the network to this end of the network was problematic. The speed of light in copper wire is on the order of 2 times 10 to the 8 meters per second. Let's see, in Back to the Future, it was 186,000 miles an hour, so 2/3 of that, 120,000 miles per hour is the speed of light, or 2 times 10 to the 8 meters per second. Well, if you do that, and your data rate is tens or hundreds of millions of bits per second, that means the time for a bit, to get sent is 1 divided by 10 million. That would be microseconds. Or, we have data rates now in the gigabit per second, that's billion. So 1 over a billion is nanoseconds. And so what happened was, in a system that said wait for the channel to get idle before sending, if the other station was really far away, you could end up in this horrible situation that you would be sending at the same time as the other station and not know it. You listen, and because that message is in flight, going some distance from Maui to Oahu, okay, from Nelsonville to Athens, from Akron to Cleveland, you send thinking that the channel is clear, but the channel was not clear. You just didn't know it because it was going to take so many nanoseconds or microseconds before that message would reach you, and that was bad. And so the upper limit on the time was based on collision avoidance, collision detection and collision avoidance, and gives us our new soon to be homework problem called propagation delay. Propagation delay is D over C, it's distance. I'm going to do metric, so we're going to do this in meters, not kilometers, not miles. And C as in equals mc squared. C is the speed of light. Okay, we can do math together. We can do algebra together. This will be fine. We're gonna measure the distance between a couple places, not in miles, but in microseconds or milliseconds. So, from Honolulu to Hilo, which I've never been, there's 200 miles, which is 2 milliseconds. But it happens that, at 1 megabit per second, which was Mr. Metcalfe's data rate when he did this project he finished in the 80s. So let's say late 70s, 80s, there were 2,000 bits in flight on the way to their destination, and they would all be damaged if two stations transmitted at once. If two stations impress on the same wire different information, they both get damaged and are not usable. They're not, we will know there's a message there, but you can't read it. It's wrecked. Okay, and so it's an interesting use case. I know it's a recording. If it's really a great lesson. This is PBL3 on constraints. Go back and listen to it again a second time. It's pretty interesting stuff. It's the last stuff in the book, but it was the stuff developed first. And these people just went from problem to problem, and I'm sure a lot of them wanted to quit, and I'm sure probably people did quit. They said, we can't solve this problem. And, to you, the distance learning, e-learning student who doesn't give up, who's given up your nights and weekends, realize that these people just kind of muscled their way through the problem and came to a solution. And that's you. And we're done. ITS 2010, Module 5, Unit 2. It's Layer 2. It's the data link layer within TCP/IP. There are other, in fact, layered protocol models. One is called OSI, for Open System Interconnect. It's actually in French, so it's whatever the French version is of OSI. But, you can't do any of this networking stuff until you can get two things to communicate between each other. I say directly, meaning they are on the same local area network, and that they're probably under the same roof. They might even be connected into the same box. They might even simply have a wire that connects the two of them together, and it's the step without which we can not build networks. We cannot do internetworking. We can't do any of that stuff unless we get two things to talk to each other. Kind of in CSM, kind of in Chapter 6, where we'll talk about CSMA-CD again. Briefly mentioning wireless, talking about the bus, hubs, and switches, going forward a little bit in switches, and pretty much that's where the content ends for the class. People started working on the link layer as the primary task. Now on slide 2, Metcalf, in the 70s, interconnecting the Hawaiian Islands using local area network technology, well before people started thinking internet thoughts. So the business about connecting printers, having centralized backups, that sort of stuff. But having intra-company email, compelling use cases that were completely justified before we invented this time thief called the internet. So the winner and champion in this is named Ethernet. Ether, at one time, before people understood radio is electromagnetic fields. They bend, they cover the earth. Before people understood that, other really smart people invented radio, had radio working. They kind of felt compelled to have a theory of why it worked. They knew it worked. They were selling ads. We had radio, we had music. And so they invented this notional material called ether that lived in the atmosphere, and it modulated and propagated the signals. And then, after Einstein, people said, never mind, all that science was wrong. And so there's really not ether there. There's really nothing there. It's actually electromagnetic fields. And then we have come to kind of reinforce this theory that not only is the nothingness in the atmosphere sufficient for propagating waves, the nothingness of space is also useful for propagating radio waves in space. We do that. We've been doing that for a long time. Okay, so I've got this thing in Ethernet. Ethernet is the standard. It is not. It is so number one that we don't even really know what number two is anymore. Probably Ethernet as a technology eclipsed IBM Token Ring in the 80s, and a lot of technology is winner take all. No prize for the losers in technology. Um, you do know that both Macs and PCs have the same chipsets on the inside, and so we pretty much have standardized on that. There's a little bit going on in some other things, but I deemed tech. If one's not careful, tech is friendly to monopolies, or at least oligopolies, small numbers of competitors. Geography makes monopolies work. So it's like, being served by one electric company, having, one railroad, having one water sewer company um, is the norm. Having one phone company is the norm. Having like 3 or 4 wireless companies is kind of like pretend competition. They compete enough um, to avoid government oversight. That's not a political statement. But the thing that characterized Ethernet on slide number 2 is the access method, which I've described as contention. Contention means fighting. Contention implies there's nobody in charge to break up the fight. And the carrier sense multiple access, or CSMACD approach exists here on the 4 bullet points. Listen, send, jam, wait. So the listen, wait till the channel's idle. When the channel becomes idle, begin to send, but simultaneously listen. Usually that's good enough, but if while you're sending you hear something else, game over. Your message has been destroyed. Stop sending. You might as well pile on and send another jamming message, and then wait, and then do it over again on the local area network. The wait and redo part is actually somewhat interesting. I think it's really mathematically very interesting, and that's, again, my take on things, that we would repeat this little process up to 10 times at each from 1 to 10. Flip a virtual or magical coin and count the number of heads. So it's like, if you flip it once, you could have 0 or 1 heads. If you flip it twice, you could have 0, 1, or 2 heads. Well, based on the number of heads in those pretend coin flips, you wait a unit of time and then do it over again. Well, you're waiting. The station at the other end, they're doing their own kind of independent coin flip things. And in terms of probability, if we're flipping 2 coins, it's only a 3 out of 8 chance that you'll come up with the same number of coins. It's a 5 out of 8 chance that you'll have a different number of heads in your coin flips, and you will delay different amounts of time. And by delaying different amounts of time, you will not collide. If I wait 2 ticks, and you wait 3 ticks, after 2 ticks I send, and you're still waiting. So we don't re-collide. It's a beautiful thing. The unit of time is beyond the scope of the class. It's 51.2 microseconds. It's a microscopic amount of time. So, slide 3, thoughtfully entitled, and other methods. Well, if we do this contention thing in the wild, by the time the channel is like 30% utilized, things are going very badly. So, in theory, it kind of worked, but, again, our approach to the science is we build it first, we assess its performance, and then try to back in and come up with a theory that explains it afterwards. And sometimes, if it works, we never come up with theory of why it works. We just leave it go like that, and it's actually really fine. Don't think that all these PhD types have everything perfectly figured out in advance and they plan it and it works, and then we move on to do something else that's genius. This is not like that at all. So, for a channel to become 30% utilized, that could be like a couple really chatty stations, or it could be like just having a lot of stations. And so, there's no intrinsic limit on how many we could have connected. Okay. we discovered that, in practice, our CSMA CD coin flip wait delay time falls apart if we make our stations more than like 1,000 meters apart. If we make our stations more than 1,000 meters apart and we're doing coin flips based on waiting, we're waiting a lot, and our channel utilization is really low, and we're not happy. Okay, so is this a legitimate trade-off? Is this a legitimate trade space between distance and data rate and algorithms? It wasn't planned that way, but it turned out that way. Okay, and so they're doing all this thoughtful thinking. They're creating the standards on the world's worst medium, which is like this surplus cable TV cable. So all these great engineering decisions are being made apparently in the 70s, okay, using the world's worst materials, and they're creating the standards. And guess what? It's like 2019, and we're using the exact same standards in 2019. The new computer, the new Microsoft Surface Pro 6 that you buy, next month is going to have the recipe, the algorithm from Bob Metcalfe circa 1972. You should not be happy about that. Or TCP/IP, circa, 1986. You should be asking more questions about that. IBM Token Ring was based on the ring topology, the turn taking, and the flooding of extra tokens onto the ring. It actually had less advanced chips, but it had more advanced thinking. IBM is still a big deal in like major finance and manufacturing and government. And it happens that, it's one thing for people encountering delays on Fortnite or Facebook. It's another thing if you've got 250,000 employees, and you've got people trying to do like cell phone configurations in kiosks and malls. And so having, the token ring approach, the IBM approach was tremendously costly. Its peak performance was never like great, but its average performance and its poor performance were completely predictable. And so we never really suffered from delay by going with this. It's not even number two. It's a trivial system, but the notion was the turn taking approach actually performed very average, and average is better than poor, and so average did resonate in certain places that had lots of customer facing employees, where employee inconvenience was to be minimized. So it has been a historic test question. The contention approach is very efficient. You don't have the expense of the device in the middle, and these things just kind of fight for access, and they keep the channel very well utilized. It's actually quite efficient, although when it goes bad, it makes everything delay. That is the single symptom. It's also not very fair because you don't know when you ask for a turn when you're going to get your turn. So the token ring approach was very fair, very average, very expensive, and it was like the big loser. So it happened that people liked the approach of contention and work it out, and it happened because they're the winner. That chip doesn't cost a dime these days. It's like maybe it's a dime, maybe it's a quarter. And the IBM token ring cards were still $1,000, and so as you can tell, 10 cents versus $1,000 is a pretty easy argument when you're trying to sell laptops for $200 that have $50 for the parts in them. The conclusion on slide number 3 is that, commerce and capitalism often are winner take all. Slide number 4. Slide number 4, we could do like an entire class in wireless. I would love to do an entire class in wireless. It happens that what we do in wireless local area networks looks a whole lot like wired local area networks, with only a couple exceptions. I study 5G. We've went from 1, 2, 3, 4G LTE now into 5G, and that's like $50, $100 a month. and a new $1,000 phone every couple, 3 years. That's a very interesting business model. You didn't know you needed one, but now you have one, or maybe you saw everybody else had one and you have to have one, and maybe you want one of these instead of a car. I don't know. But what I will say is that the wireless network that's in your computer that you can attach on at, McDonald's, Panera, Starbucks, Kohl's, Walmart, Ohio University, EduRoam, any university, and I should mention that your Ohio U login avails you to a service called EduRoam, EduRoam. So if you are doing your studying at a different university, you can certainly get on their EduRoam network if they are an EduRoam institution and use your OU login. In the course of a week, I am often at several other institutions, and I'm often on EduRoam. Okay, so 802.11 wireless LANs are not licensed. They are free to use. The hardware is like built into our devices anyway. So your $40 burner phone at Wally's has got a wireless chipset in it to support 2.4 and maybe 5 gigahertz. It is possible to use it as a point-to-point backhaul, known as infrastructure mode. It's rare, and even when it does exist, it's not open to you. There's also an ad hoc mode used for wireless access, which is where you attach in your dwelling, or at your workplace, or where you go to travel. And it's kind of two modes. It is over time a mixture of contention, because it's like, you can authenticate with it, you can perhaps log into it, but you can certainly tell the access point device when you have something to send, and it will acknowledge your request and in turn give you a time slot or a time slice to go send something. So so the wireless access points, and you've seen them, they are in ceilings everywhere. I will challenge you, not in the outdoors, but on the indoors, grocery store, retailer, restaurant, mounted to the ceiling, generally. Antennas facing down, that's fine, that works. Doing the version of CSMA called CSMA-CA. It's got a little bit of polling, a little bit of contention, no sharing. It's an Ethernet in that it's a single radio channel, just like bus Ethernet on coax, just exactly like bus Ethernet on coax. Okay, so the final point before moving off the wireless slide is that, in the U.S., the Federal Communications Commission will regulate all wireless emissions. You will license some things. Your cell phone actually is operating under a license issued to AT&T or Sprint or whomever. The wireless stuff for like 802.11 wireless LANs is regulated but not licensed. And that's a problem. I'm certain that on your phone or your laptop or whatever, you will get to peruse the long list of wireless networks available. And it's a really long list, and you only see the top of them. It would be that if you're traveling, so I turn it on wherever I leave a place that I will turn it on in a place that I trust, like home or work, or maybe some establishments. And then I turn it off, especially in the car. It sucks the battery, it draws the battery down. So a couple points about radio, real quickly. That there's only like 11 channels in wireless, and they're constantly being reused. Your cell phone has got about 800 channels that it can use. In the geography matters, the FCC, when the FCC makes an effort to work with service providers to allow the geographic usage of a single frequency to be maximized, but then beyond its maximum it gets reused. There's a limited number of channels, and they will alternate them. We have, in our wireless world, we only put our access points on channels like 1, 6, and 11. And so it's 1, 6, 11, and then the next floor up it's 6, 11, and 1. And then the next floor up it's 11, 1, and 6. So we never have the two stations on the same channel adjacent to each other. The FCC does not get involved in the siting necessarily of the towers. It licenses them, but it's up to the company to propose whose rooftops to use and where to build towers. And it's kind of neutral on the underlying technologies, which is why we have both GSM and CDMA phone providers through LTE. In 5G, we won't. And it's just interesting in the wireless LAN space. You could put like a doorbell or you could do anything on these frequencies, and because they're regulated but not licensed, there's not a heavy hand on that. Okay, slides 5 and 6, really important stuff. Let's pay attention. I know we're a little bit long with this, but I think it's essential stuff. The notional Ethernet bus is the concept behind all Ethernets, whether they're wired or wireless. And just the difficulty of working with coaxial cable, the brute ugliness of dealing with coaxial cable made it pretty unpopular. The alternative, this goes back to my career when we deregulated the phone companies. We used to have this model of having like phone extensions, and the phone extensions in a business would all be wired back to a private phone switch that would be sitting in an equipment room or a closet. And so that was a star topology. So how do we take like a bus technology and make it run on a star? Well, the prize was if you could get the computers to work on the wires built for the phone network, then you save like $1,000 per station. You could really accelerate the adoption of local area networks on computers if you could make them run on the phone wires that were built in for phone extensions. Now, if in most places where you work, you'll have like 3, 4, 5-digit dialing within the company. That's because there's like a phone switch that's inside that company's premises someplace, and you're wired from this phone. Maybe I'm an extension 123, which is sitting on my desk, wired directly back to this phone switch thing, and I can call extension 234 with 3-digit dialing. You might have not ever seen that. That some places you don't have phones on desks. I know that in the age of dormitories, we used to have a phone in every dorm, and they had 5-digit numbers and a paper phone book. And now we might have one phone per floor simply for 911 emergency usage. So firms that desired wiring that could support LANs based on the business phone system, they were stars, they were unshielded twisted pairs, maximum length 100 meters. And we had categories 3 and 5 and 6. And so basically we took the Ethernet bus and collapsed it into something that looked like a star and invented, first of all, this thing that looked like a hub. We don't even want to talk about hubs. The hubs, you really can't even find one to buy one, but this hub was a very important intellectual step because it took the Ethernet bus, the single channel, and turned it into an Ethernet bus that ran through this thing that looks like slide 1, looks like this little pizza box with the 24 ports on it. Well, in the thing called the hub, the 24 ports were a single channel. Everybody heard everybody else's business. And had all the drawbacks of the CSMA CD Ethernet, like, when utilization hit 30%, the delays started to increase without bound. Simultaneously, and I'm still on slide 5, simultaneously, Moore's law is advancing, which means we have more and more processing power every day, every week, every 18 months. So somebody said, well, why don't we put a computer in every one of those devices as shown on slide 1 of unit 2 here today, and only pass traffic between the two physical ports that are in conversation. Well, before all that box needed, the box before really didn't even need any electricity at all. And at this point, this device, if we put processor in it, if we gave it power, if we wrote it a little program, what would the program do? The program would say, if the conversation is between jack 2 and jack 8, then we're only going to pass the traffic between jacks 2 and 8. We're not going to bother the other 22 ports. Pretty amazing stuff. If the traffic is going between port 2 and something that our box here is connected to, then we will send it to one of the egress ports. If you look at closely at back to slide 1, there's like 24 ports on the left in 2 rows, and then there's 4 ports to the right, which are uplink ports. They're used for ingress and egress between the star represented by this switch and whatever else. So this thing might be sitting like in the 3rd floor of Schoonover Center where my desk is. And it's like its version of the uplink is the main building switch, which is sitting in the basement. And so that main building switch is going to talk to all the floor switches. And its version of the uplink is to go from Schoonover Center to the Office of Information Technology presence in the library. I hope that makes sense. How do we do this? On to bullet number 4 here, the Ethernet switch. We're going to introduce the notion of a switch. Layer 2 has a thing called a switch. It contains logic that will only pass messages between 2 select nodes, between 2 select ports, between 2 select jacks on that thing shown in slide number 1, looking at the layer 2 destination address, which is in the header. That header is referenced in that slide 2 of the Unit 1 thing from the prior recording. So looking at that address, it says I'm only going to forward it where it needs to go. In fact, it can forward it as soon as it's looked at the address on the envelope. It doesn't need even to open up the envelope and look at the message on the inside. That's good because we might even encrypt it so it can't see it. And so that's really where I should stop because this is momentous. This is exactly what we do. We do wireless, but the wireless presents itself into one of the jacks on the switch, as you see in this picture. And then based on the destination address, the traffic is only shared with the port representing that destination address. And if it's outside that box, then its egress is through the uplink port. Pause, deep breath. Deep breath. A switch is kind of what a traffic circle is to a hub. And the notion of a switch is we can have a lot of conversations going on at once. I would hope that by now you've seen a traffic circle, maybe gained the confidence to drive through traffic circles. You can actually have a bunch of cars in a traffic circle at once. Admittedly, the OU traffic circles are pretty small. In other places like Talmadge or Dublin or like Boston, the traffic circles, DC at DuPont, are really big. And you can have lots of cars in the traffic circle at once. They enter on the route that they enter, and they exit on the route that they exit, and you're really not supposed to go around the traffic circle more than once. We will say that, generally you don't have to wait long to get onto a traffic circle. Compared to a traffic light, it seems like there's some lights I wait and wait and wait. A traffic circle I can pretty much get on pretty quickly and get off. I don't have to wait for access. It happens that, compared to traffic lights, traffic circles or roundabouts have fewer collisions. You'll have to take my word for that. Obviously, the people that encounter traffic circles and roundabouts for the first time are often the cause of accidents. Okay? But in general, left turns and traffic lights are unhealthy, and we just simply don't have that in this. Point number 6, and then we're done, our denouement. The switches themselves can be networked. We can create a network of switches. In fact, we really love that mesh topology. So we can physically build a mesh topology out of these switches, so they have more than one way to get from anywhere to anywhere. We can even use switches to do something that looks like a ring. A ring would then be kind of a subset of a mesh. It happens that physically we can interconnect them mesh-like, and logically an algorithm that is automatic, that requires no human intervention, can create this mesh, can take the physical mesh and turn it into a logical tree only by pruning the branches that would cause loop conditions. And what's even better is if somebody breaks it, if somebody breaks a link or something goes away, then immediately the switch will heal the network by creating alternate branches on this virtual tree to get from any point to any other point. Yeah, I mean, we studied that in layer 3 with great pain in regard to interior routing, where we either talked to our neighbors or talked to everybody, and it was complicated and it was chatty and there were problems, and it required humans. And layer 3 required addresses and thoughtful thinking in humans and algorithms, and the switches don't need any of that. The switches just kind of plug them in. You can be somewhat indiscriminate in whether you've created, duplicate paths to things, but these switches themselves contain advanced algorithms, one that's called spanning tree, that will create a logical tree out of a physical mesh so that there's one and only one way to get from any point to any other point. To be specific, one node becomes designated the root node for the tree, and the election that you never ever see in the paths that you cannot ping, that you cannot ever see, just kind of do it automatically. So, a thoughtful question will be, well, it took a lot of work to make all that layer 3 stuff and created a lot of careers for people like ITS graduates. And doesn't that all go away if we do layer 2 switches that do spanning tree? It kind of goes away, but we have enough work to do. It kind of goes away, but those were jobs that we didn't really want, so most of those did go away in layer 2. I mean, layer 2 kind of did so well that, we let it escape the building, that we now can have a layer 2 switch relationship with service providers like AT&T and Spectrum, level 3, Everstream, that the service providers can get rid of routers too. They can say, well, eventually, you need to have addresses so you can interconnect with the outside world, interoperate with the outside world. But we're happy to connect you at layer 2, which means we will pass frames, and we just have these switches that will make sure that things go where they need to go. We can, again, I'm on the second bullet on slide 6, we can create LANs based on membership. We can say, well, these people work in the accounting department, or these people work in the admissions office, and they're all plugged into the same device, but we're going to create a private entity for them, not only in this building, but if, let's say, they got people over in some other building or some other city, we can create a membership-only LAN based on which ports they're plugged into. Now, we can't give it like a meaningful name like admissions. We would give it a number between 1 and 2 to the 10th, 1024. But that's where we have such great flexibility to have much better control on who's in and who's out. It's not glamorous work, but it's truly effective, and the customers like it. And we're even able to extend this private notion of local LAN membership with the cooperation of our service providers to other locations. And so it's the virtual LAN or VLAN, and then we can create VLANs that will go over several sets of switches, and those switches can be in different places with full cooperation of the service provider. And it takes an administrator to kind of select which ports, to identify which ports. Kind of a case in point is look at a major retailer or a hospital. There's a lot of different business units operating under the same roof. So let's say that this is a typical, or the radiologist or the lab in a hospital might be its own corporation. And it's like, well, they have people here and there in the hospital, or let's say somebody's going to remodel. It seems like hospitals constantly are remodeling. And so we'll leave the wiring in place, but the port numbers associated with the individuals and the computers for that entity will be segregated and organized into their own little virtual local area network. I wish we could give them meaningful names. Instead, they just get a number. And maybe that's what keeps ITS grads in business. We've got secret spreadsheets that have the membership groups of these virtual local area networks, but it's all for good. And this, we can thank Moore's Law for this, because as we have added compute and storage capability to our devices, we are much more granular in our control over networks, which is good for security, and it's good for employment. Thank you. One more to go. Welcome back. ITS 2010, Module 5, Unit 3, we're done. We have just a little bit of things to talk about in our concluding lecture for this class. Hard to predict the future is. My prognostication is based on trends that I've seen, and perhaps even by the time you play this back and hear this, I can be proven wrong. Happens quite a bit. A lot of what I do is not based on math skills or, engineering skills or things like that. It's about having trusted, authoritative sources and kind of listening to them. I've taught for many a year, and as my students become, professionals and in their own way teachers, I think we're not just hungry. Sometimes we're greedy for information and can highly value the best information. Well, the descendant of AT&T, Alexander Graham Bell, Watson, come in, I need you. That company has not fared so well, and not in their defense, but they split the company up three ways, and they said, we don't really want these local companies. We want to be in the long distance business, and we don't want to be in the equipment business. Well, equipment wouldn't have been half bad. There's been some very successful equipment companies, but the geographic monopolies that run phone companies, they deal with people where they are, and the access from people where they are has gone from wired to wireless. It's gone from voice to data, and it's like that would have been like a really great bet. And like, I'm not sure how long it's been since I've paid a long distance bill. I think my cell phone stuff and my I do have, for 911 purposes, a wired phone at home, even though it's voice over IP. It's like, being in the long distance business was probably the wrong thing for AT&T to do. But AT&T's equipment descendant, first went to the French, which is Alcatel. That now has gone to Nokia, which is from Finland. And Nokia is the owner of Bell Labs, which is literally where the only Nobel Prizes in telecom have ever come from. I've been privileged to have visited there, to have professional relationships with some folks who've been part of that world or are still part of that world. And it's not the people so much that I really am interested in what Bell Labs still has to say about telecom. A book I'll recommend is The Idea Factory, which takes us through the vaunted history of the labs. And Mark Weldon, did a book on the future of these things, and I would encourage you to, listen to their forecast of where these things go. So, Unit 3, 6 slides, concluding with the ever-popular conclusion and next steps sorts of things. Talk about the state of the market, talk about provider networks, talk about, where the processing takes place in this stuff. And then we kind of end back at the beginning. Slide number 2, from and to, pretty non-assailable. A couple metrics that I think worth looking at. First we built for voice, for telephony. Now we're optimized for data. To go from 4G to 5G, takes us from a network that was voice with kind of an add-on to a true data network where voice is just an app. We've gone from having a lot of dedicated, non-shared, specialized, private physical networks for every one of the Fortune 1000, and then some, to everybody just kind of running stuff across the internet. Running things across the internet requires encryption, but we've gone from like $1 per megabit per second per month, if not $1,000 on the order of $1,000 per megabit per second per month, to like under $1 per. I mean, so we have gigabit service under $100 in several places around the country. When we dealt with scarcity, there was finesse and nuance and attention paid to classification of traffic. We had jobs for engineers. Okay, so we have abundance, and the stuff runs so fast with such great capacity. We really don't have to engineer things so much. It's a debate within the community whether we're spending our time on the right things or not. We've gone from enterprise apps located in the computer room, at headquarters, to a lot of stuff that resides only in the cloud, primarily Amazon Web Service, Google Cloud Services, Microsoft Azure, which is French for cloud, and there's a lot of local providers that do cloud hosting as well. We've gone from copper private networks that operated at layer 3 and used routers for interior routing, to fiber networks that are running layer 2 and VLANs, etc., to the remote sites. Another take on that same thing is we would have like routers and cell base stations and mobile networks. And now we run fiber to the base stations, and by the time we fully get into 5G, it'll be a layer 2 fiber optic handoff. There won't be as much stuff in there. You go by a cell site today, the air conditioner's running, and the buildings are so full there might be 2 or 3. There'll be a cabinet, and one set of sectored antennas, and hopefully a backup power source of some sort. Routers as the gateway of networks have kind of fallen away to switches and VLANs, but I should caution you that the things that look like routers have gone away, and the things that exist look like switches, but the granularity of processing, that's a word I'll use here and there, the specificity, the detail involved in making forwarding decisions takes place in a switch. Is it switching? Is it routing? Is it something else? Is it policies? Routers is the gateway to networks. Switches and VLANs, policies, granular decisions. Slide number 3. The provider networks were designed for the public switch telephone network circuits. And those circuits took packets, and now we're going from the circuit-based world to purely the packet-based world. We did expect, on copper there actually were a lot of errors. It was like 1 in a million. Now we're like 1 in a trillion, and there are things you just don't have to do when there aren't errors quite so much. Cars used to last 75,000 miles. Mine's got 275,000 on it. There are things that we don't have to worry about when the reliability is high. We don't really know what the next thing is going to be, but generationally, a lot of adoption for a lot of attraction to video. What is TikTok? What is the appeal? People love it. In a process that's mobile first, probably is more like non-US than US, but looking at demographics and people's media choices and affinities, it's a mobile video world. Slide number 4. We must, in an internet technology class, encourage proficiency and competence in layer 3 routing. A lot of people think layer 3 routing and addressing are the fundamental discipline in my particular department. If you were in my department, you would hear that stated a lot. And 10 years ago, it would have been all about that. 10 years from now, probably not. But, layer 3, has been doing kind of policy-based routing on a per-site basis on the interior. Layer 3 on the outside used kind of a brute force approach to on a global basis on exterior routing. I don't like to do like timely news sorts of things, but in my night class, we were scheduled to take an exam at 6 o'clock via Blackboard, whether you were on global campus or whether you were in the room, and Blackboard failed at 10 minutes beforehand as a consequence of a misapplied configuration in their BGP exterior routing setup, which was actually really bad. Um, I don't think anybody felt better that it took place, although I had to dismiss class and allow people to take it at their convenience outside the classroom. I don't think it affected any outcomes, but it was not. It was a bad situation. The the emerging approach to forwarding decisions is going to be per keyword switch port. Every one of those little jacks in the picture on slide 1 from Unit 2, is going to have a bunch of policies around it. It doesn't have to be bound by, what address is on that machine. It can be part of a group that spans that device, others nearby proximate to it, others on the campus, others connected by provider networks anyplace else. We can have a very granular policy set up for the membership in virtual local area networks based on their membership, having policies regarding to their privacy and security, and we can even kind of optimize it based on what that port is being used for. Interactive video conferencing is probably the harshest thing we do, short of like Wall Street, flash trading, stock trading, or like telesurgery. I mean, those would be like really robust use cases. But for the kind of stuff that we do, I mean, we could configure it differently, whether it's a surveillance camera or a doorbell, or an email kind of general purpose workstation, or bioinformatics. I mean, we could have policies that would be very specific and granular to that port in the club that it's a member of. Slide number 5. Well, our world used to be organized around some very small lot, high dollar chipsets that were only used, in a couple applications. Low volume, high cost, high lead time. They would be on circuit boards that would have a very proprietary operating system. The expertise for that was rare and generally highly valued. Because it had a small user base and the people were kind of in the club, the interaction with it was clunky and prone to errors. And it was developed in an era that really didn't anticipate, the proper level of paranoia in security. So it's like it kind of expected that you would be right there, and everything else remotable was kind of assumed that you were right there, which was really horribly not secure. So the emerging generations for doing networks use Intel chips. They're called white box or bright box. They have web kind of not drag and drop, but graphic user interfaces. Very low error rate, very easy learning curve. To some extent, because of the way they developed, and because the hardware is like free, the software. Some of the versions of the software are used by experimenters and they're free. It's very disruptive. If the prior device cost $250,000 and this one cost $25,000, that's very disruptive. It does affect things. I visited the school where I attended way back, and they had replaced their $250,000 items with $25,000 items, and we're very pleased with the outcome. It was a different vendor. And it's at that point with such little money changing hand, it's hard really for anybody to make claims about whether there's enough profit in it to keep that company in business in that line of work. It's commodity operating systems like Unix can ideally configure from anywhere, and it will happen that the basis for 5G is along this product line. That it happened that when Verizon wanted to do the next generation of public safety nationalized, they wanted to use kind of the old school equipment, and it would cost way too much. And AT&T did receive the contract to go build it, and it is building out all across the country. Um, you care about it because it's rolling out as public safety, and it will be kind of dual use, repurposed for commodity commercial wireless subscribers, and it's based on this open source software community and Intel chips. And we kind of thought we'd be seeing more of that this year, but it has been somewhat delayed for security reasons, and we do expect to see the promise of 5G met within years in the U.S. So wrapping up. It's been a good semester, folks. I admire what you do to take time that you would have, could, or should have spent, with those around you to manage multiple responsibilities at the same time. I admire that, and I wish you well. Moore's Law has not stopped. It will not stop. The doubling of electronics every density, or the halving of the cost every 18 months, kind of defies the laws of physics, but it keeps going on, which means the changes will not stop. The trend lines will continue in the direction that they're going. The electronics and telecom products that are tied to Moore's Law will find the declining marginal cost year over year, except when it's more rapid than that. Mr. Weldon, from Bell Labs, Dr. Weldon, Mark, he's already talking about 6G. The 6G world, we can't tell where Wi-Fi ends and subscriber wireless begins. That's good because when you're on Wi-Fi, under the right circumstances, you can generally expect much better performance, but there's no money in it. And then the Wi-Fi part, they're cutting their cost by going to open source, white box, bright box, Intel, Unix, but they make their money by charging you $50 to $100 a month and hoping you exceed your data cap. So we'll see where that goes. The 6G world is already on somebody's whiteboard. The Bell Labs thing, which I'm fond of, and we wouldn't be here today if it weren't for Alexander Graham Bell and AT&T and Bell Labs, and as somebody as all of us, as people who value the credential and value being part of something great, we do need to look carefully at these true institutions in what we do. You want Ohio University, to still be in business 50 years from now. You want that degree to be worth something. We want the telecom industry to at least have some level of viability. So apparently, like getting a bunch of Nobel Prizes is not a guarantee. Trying to game government regulation does not seem to be a great strategy for success. Businesses fail. Okay, and so let's not go there. I'm not really predicting anything. We look at Amazon likely to be split up between its retail kind of consumer-facing things and its outsourcing of cloud services and applications. There's probably a lot more value in Amazon in pieces than put together. Google, nobody quite exactly knows what they do. Both Google and Facebook, have been incredibly successful financially, both through stock appreciation, capital, and operating the ad kind of businesses have been pretty well. They've kind of operated in ways that, in hindsight, think might have benefited from a more adult supervision that might come at the hands of EU government or the U.S. government or something. So policy, sometimes there's a balance when the market forces don't give the kind of outcomes that people perceive as fair or honest. And really, there's going to be a next thing. I think some of you, having read your essays, could be that person. It's a whole lot more working nights and weekends, giving up in order to get something going in the future. But if there's one constant in this business, it is change. If there's one thing that I could pass along is continue to learn, continue to care, continue to keep your mind open to these things, and you are fully empowered to go invent and go create and make things better. Thank you for attending ITS 2010.